The seatback map shows a straight line from New York to London. The plane is not on it. It's arcing north, curving up toward Greenland, tracing a path that looks longer than the obvious route sitting right there on the screen. Why would a pilot choose the route that looks longer? Who decided a curve beats a straight line? And what math says that's true? If that arc really is shorter, why does every flat map make it look like a detour? And if the Earth's shape is doing this to every flight, what else are flat maps lying to you about right now? The shortest path between 2 points on a sphere is called a great circle route. It's the path you'd get if you stretched a string tight between 2 pins on a globe. Do it with New York and London, and the string arcs north, over the North Atlantic, pulling toward Greenland. That arc is approximately 5,570 kilometers. The straight line you draw on a flat map, the one that goes right through the middle of the ocean, is roughly 6,300 kilometers. That's a 730-kilometer difference. That's roughly the full length of Ireland, flown for free on every single transatlantic crossing. The viewer knows the number is real. They don't yet know why. Every map you've ever used showed distance and direction in flat two-dimensional space. GPS draws straight lines. Road maps draw straight lines. The brain matches the pattern. Straight line equals shortest distance. That logic is correct. On flat surfaces, it has always been correct. Mercator projection maps make it feel even more obvious. Mercator was literally designed for maritime navigation. Sailors used it for 4 centuries. It must show accurate routes, so the arc looks like a mistake. It looks like a deviation from logic, not an expression of it. But here's where it gets complicated. If the flatline route were actually shorter, airlines, who weigh every kilogram of fuel before departure, would fly it. They don't. Not one airline on Earth flies the flat straight line across the Atlantic. Every single carrier, every route, every decade arcs north. That's not a coincidence. That's the geometry forcing their hand. The Earth is a sphere. A sphere has no flat surface. The moment you force a sphere onto a flat map, something distorts. Always. No exception. On flat ground, the shortest path between 2 points is a straight line. On a sphere, the shortest path is the arc you get when a flat plane cuts directly through the center of the sphere. That cut traces a great circle, and every great circle on a sphere is as straight as geometry allows. This is the part everyone misses. The arc on your seatback map isn't a detour, it is the straight line. The map is the thing that's bent. When the pilot turns north toward Greenland, they aren't flying north, they're flying straight. The map just can't show it. Now add the Mercator problem on top. Gerardus Mercator published his projection in 1569. It preserved compass angles, which made it perfect for sailors holding a fixed heading. But it did this by stretching land and ocean toward the poles. The further from the equator, the more the shapes bloat. Greenland on a Mercator map looks roughly the same size as Africa. In reality, Africa is 14 times larger. 14 times. Africa could swallow Greenland more than a dozen times over and still have room. That same polar distortion is warping every route you look at on a flat map. The straight line you draw between New York and London on a Mercator projection is already a curved path on the surface of the Earth, longer than the arc it appears to shortcut. The straight line on a flat map isn't neutral. It's already bent. The map bent it before you even looked at it. The arc is the correction, not the deviation. The fuel math makes this concrete. Modern long-haul aircraft carry between 150,000 and 200,000 kilograms of fuel for transatlantic routes. That's roughly the weight of 200 fully loaded cars sloshing in the wings. At approximately 60 to 80 cents per kilogram, that 730-kilometer difference translates to somewhere between $60,000 and $90,000 per flight. An airline running 10 transatlantic crossings per day saves close to $250 million annually just by flying the arc instead of the flat line. That's not academic. That's a fleet of new aircraft, paid for by geometry. So that's why the arc looks wrong on your seatback map. The map is the mistake, not the route. Here's where it gets complicated in a different direction, because great circle routing isn't the only reason flights arc north. Passengers who know a little aviation often conflate 2 separate forces, great circle geometry and jet stream routing. Both push planes north over the Atlantic. Both save fuel. On a map, they look identical, but they are entirely different things. Great circle routing saves distance, about 730 kilometers on a New York to London crossing. Jetstream assistance adds speed, up to 320 kilometers per hour of free push at altitude. the equivalent of strapping a second engine to the fuselage without burning a drop of extra fuel. A westbound flight fighting the jet stream can take 13 hours. The same aircraft, eastbound, riding the jet stream, covers the same Great Circle path in under 7 hours. That's nearly double the time for the same route, depending on which direction you're flying. Great Circle routing is about geometry. Jet stream routing is about energy. One is fixed by the shape of the planet. The other changes every day and must be replotted every single flight. The difference isn't which direction the plane arcs, it's why it arcs. And every day over the North Atlantic, dozens of aircraft fly nearly parallel paths between 50 and 60 degrees north latitude, separated by precise vertical and lateral spacing on a set of tracks called the North Atlantic Organized Track System, replotted every 12 hours based on where the jet stream moved overnight. Who decides which tracks exist on a given day? Shanwick Oceanic Control in Ireland and Gander Oceanic Control in Canada do, simultaneously, before dawn. And what happens if the forecast is wrong? That's a question with a very specific answer that doesn't end well. Here's where it gets crazy. May 21st, 1927, Le Bourget Airfield, Paris. A crowd of 150,000 people is standing in the dark, waiting. They have been there for hours. Some have been there since afternoon. Then lights appear low on the horizon, slow, uneven, unmistakable. Charles Lindbergh lands the Spirit of St. Louis after 33.5 hours in the air, and the crowd breaks the barriers and swarms the plane. He covered 5,808 kilometers, solo, non-stop, the first person to do it. He had no radio, no GPS, no autopilot, no co-pilot, no instrument to tell him whether he was drifting east or west over 3,000 miles of open ocean with nothing below but black water. What he had was a 30-centimeter globe in a hotel room in New York. He used it to plan the route. Not a flat map, a globe. He stretched a string between New York and Paris and traced the arc it made, then transferred that arc onto navigation charts by hand. He flew a modified Great Circle path and corrected it in real time with a magnetic compass, dead reckoning, and star navigation when the sky cleared enough to see stars. 1 degree of drift per hour for 33 hours compounds to hundreds of kilometers of error. He landed 8 kilometers from his planned touchdown point. 8 kilometers. After 33.5 hours over open ocean with none of the tools a modern pilot has, he hit his mark to within the length of a small town. Lindbergh's flight didn't just prove transatlantic aviation was possible, it proved Great Circle navigation was operationally viable, which directly shaped every long-haul routing standard built after it. That flight is why transatlantic routing is built on spherical geometry, not map geometry, and why pilots still learn Great Circle principles before they ever touch a flight management computer. Here's the surprise. This system has been running around you the whole time, and once you see it, you can't unsee it. Every time a flight from New York to London shows an arc on the seatback map, that arc is the straightest line physics allows on a planet that isn't flat. Every time a transatlantic passenger looks down and sees Greenland through the window, they're passing over it not because the pilot took a detour, but because Greenland sits directly on the shortest path between those two cities. The globe put it there. When a flight from Los Angeles to Tokyo appears to cross Alaska on the route map, Alaska isn't a stopover, and it isn't an obstacle. It's the geometric center of the shortest path between those two cities. That one surprises people every time. When an airline shows a flight time of 7 hours eastbound New York to London and 9 hours westbound, the pilot isn't flying a different route. The jet stream is adding or subtracting 2 hours on the same Great Circle arc, depending on which way the wind is blowing. When air traffic control assigns North Atlantic Track Bravo at flight level 360 to a pilot, that track was calculated before sunrise by 2 oceanic control centers on opposite sides of the Atlantic, simultaneously optimizing for both geometry and that morning's jet stream position. When a flight from London to Singapore appears to fly west over the Middle East rather than straight east, it's still following a Great Circle arc. The Earth's curvature just makes flying straight east the longer option. When polar routes over Russia opened after the Cold War ended in the 1990s, airlines weren't discovering new shortcuts. They were finally allowed to fly the Great Circle paths that had always existed over Soviet airspace, geometrically valid for decades and politically blocked the entire time. When GPS satellites calculate your location, they're doing spherical trigonometry, the same mathematical family as Great Circle routing, millions of times per second for millions of devices simultaneously. When a child draws a straight line between two cities on a globe with a marker, they've just plotted a great circle route. They understood the geometry before they knew what it was called. Then there's this. When engineers laid the transatlantic communications cable on the ocean floor, they routed it along a great circle arc. The internet running under the North Atlantic bends along the same geometry as the flights crossing above it. The cable teams and the aviation engineers didn't coordinate. They both followed the same shape of the planet, independently, and ended up in the same place. When a ship navigates from Cape Town to Sydney on a great circle course, the route goes south, deep into the Southern Ocean, close to Antarctic waters. Shorter, colder, more dangerous. Some ships take it anyway. The geometry doesn't negotiate. Spherical geometry is one force. The shortest path between any 2 points on Earth is always a great circle arc, fixed, non-negotiable, built into the planet before humans arrived. Flat map navigation infrastructure is the other force. Aviation charts, airspace sector boundaries, air traffic control systems, and passenger displays are largely drawn on flat projections. The entire global network of aviation communicates in coordinates and headings that work correctly at local, short-range scales, but make great circle paths look curved when viewed from a distance. Neither rule is wrong. Spherical geometry is physically correct. Flat map systems are operationally correct for the short-range work they were designed to do. Every long-haul flight exists at exactly the intersection, flying a path that is geometrically straight but visually curved, inside an air traffic system that is locally flat but globally spherical. One aircraft, two geometries, both applying at the same time. And here's how that tension is finally starting to resolve. Pilots don't fly pure great circle paths. They fly a series of fixed waypoints loaded into a flight management system, a chain of geographic coordinates that approximate the arc in straight-line segments, like connecting dots on a curve. Each segment introduces a tiny deviation. Over 10,000 kilometers, those deviations accumulate, the way a small steering error compounds over a long highway until you're 2 lanes over. Modern FMS systems correct for this continuously, but the underlying infrastructure, waypoints, airways, sector boundaries, is still built on flat map logic. The innovation closing the gap is called performance-based navigation. It allows aircraft to fly curved path segments rather than straight waypoint-to-waypoint legs, which means the FMS can command the aircraft to track the great circle arc continuously instead of approximating it. Airbus and Boeing both support continuous great circle tracking in their latest FMS generations. On the A350 and the 787 Dreamliner, the system recalculates the optimal great circle and jet stream combined path in real time, adjusting every few minutes for wind changes at altitude. But oceanic airspace is still managed in fixed track systems, partly because radar doesn't cover most of the Atlantic. Until satellite-based ADS-B coverage is fully integrated, geostationary ADS-B became operational over the North Atlantic in 2019, but complete flexible rerouting over open ocean remains partially constrained. Truly dynamic real-time. Routing at altitude stays limited. The trade-off is shrinking. It hasn't disappeared yet. Every arc on every flight map is a straight line, the straightest one physics allows on a planet that isn't flat. Every transatlantic crossing since Lindbergh in 1927 has traced the same geometry that was written into the Earth's shape long before anyone flew it. The arc was always there. Aviation just learned to follow it.